There are only two link state routing protocols in the world that are considered mainstream, popular, in use in major organizations, and that is OSPF and ISIS. Now, we've already talked about OSPF. Pretty cool protocol, pretty flexible, a lot to it. Now let's talk about ISIS, the alternative to OSPF. Now, ISIS is a mind blower, meaning a lot of people wonder why it even exists in the first place because it was never really even designed for TCP/IP. If you can believe that. It was never designed to support the kind of networks that we have today. Why is it even there? And why is it the preferred routing protocol of internet service providers, huge ones with enormous networks? Well, that's what we're going to find out as we walk through this video. We're going to find out what is ISIS. We'll look at it in all its glory, tell you where it came from, its background, how you should design an ISIS network, and then finally we're going to take a look at a line item by line item boxing match comparing ISIS to OSPF, and then we'll see which protocol you think is better by the time it's said and done. Have you ever owned a VCR? You know, before DVD players took over the world, we had these things called VCRs that took tapes. Well, if you remember back in the days of VCR, there were two major formats for the VCRs tapes that started off with. There was VHS and there was Beta. Now, this competition was fierce, and I remember going to the video store, and they would always have a selection of VHS and a selection of Beta of which one, people wanted to use. And in the end, VHS won out. Beta just kind of dissolved and went away, but not many people know that Beta was actually the better format. I'm not too sure why VHS ended up winning. Now, here's a shocker not many people know. You know the OSI model? The one you learned when you got into networking and had all the acronyms to remember the layers and the functions and all that. Well, that OSI model was never really designed to be just a model. The OSI model just happened to be designed by the same people who created the OSI protocol that was designed as an alternative to TCP/IP when the internet was first being developed. Amazing. Imagine that there was this person sitting there, or a group of people sitting there when the internet was first developed, and they were comparing TCP/IP and this OSI protocol, and they ended up saying, well, let's go with TCP/IP because it's a little bit simpler, and I mean, good grief, how many addresses are we really going to need? Because OSI actually used hexadecimal addressing and provided a lot more addresses than the original TCP/IP that we use today on the internet everywhere did. And it's kind of ironic that they chose to go with TCP/IP, and that's now TCP/IP version 6, which is coming out and trying to take over the world, looks very familiarly like the original OSI protocol did. But that's besides the point. That was the competition that happened when the internet was born. There were some other protocols that were drafted and proposed as well, but OSI, the protocol, not the model, and TCP/IP were really the two contenders. Now, in the OSI terminology, there is no such thing as a router. Well, there is a router, but it's not called a router. It's called an intermediate system, or an IS. So this routing protocol that we know as ISIS was just a protocol that could move data between routers, and the name really describes it. IS to IS, intermediate system, or router to router, is what this protocol did. Now, that protocol was originally created for the OSI protocol. ISIS was like OSPF is to TCP/IP. Kind of had OSI protocol equals ISIS. TCP/IP equals OSPF. Now, my thought is that if that's where it would have been left at, ISIS wouldn't even be a topic today. It probably would have died on some drawing board next to the OSI protocol. And when we chose to go with TCP/IP, all of OSI stuff would have just been scrapped. But the government wasn't sure. I mean, OSI was a big contender. They didn't know whether they were really going to use TCP/IP or go with this OSI protocol. So they mandated that all ISPs would use both. The original ISPs that were created ran both OSI and TCP/IP until a victor was decided. So OSPF and ISIS were used as routing protocols in those environments. And some ISPs, even though TCP/IP won out, some ISPs said, you know what? This protocol is really good. We like ISIS. So maybe we can somehow make ISIS work for TCP/IP. And that's what they did. When the original ISIS specification was modified, it became something known as integrated ISIS, which could route TCP/IP. So the original ISIS was tuned in order to work with the TCP/IP protocol. Now, I did want to make sure I mentioned, once again, the word tuned, as it is still the same old protocol. It's still ISIS. It's still designed for OSI, but it was tuned. It was tweaked. It was modified to run TCP/IP. The reason I emphasize that is one of the things that you'll have to understand in order to make ISIS work is how the OSI protocol addressing works. It's odd, but you do still have to assign an OSI protocol address to your router in order for ISIS to work, even though it's been tuned to work with TCP/IP. Now, here's the facts. Let me just dump the facts on you about this protocol. Number one, it is a link state routing protocol. So everything that is link state belongs to this. It has the tables, neighbor table, topology table, routing table. It's got the SPF algorithm that it uses. It forms neighbor relationships with the hello messages. I mean, everything that we talked about when we talked about OSPF applies to this. The concept of areas. It uses area concepts. Now, here's some interesting information. ISIS is more tunable than OSPF. It has more areas that you can tune. It is more efficient than OSPF on your router's resources. I'm talking memory and processor utilization. It is more flexible than OSPF in how you can design the network. The big thing being the backbone area. In ISIS, there is no backbone area. There is no area 0 that everything has to connect to. That is what allows it to be more flexible. We'll talk about that a little bit more in a bit. But the bottom dash that you can see on the screen is why it is not the more popular routing protocol. That is because it is much more difficult to understand than OSPF. Now, I don't want you to start quivering right now because I know OSPF is pretty intense. ISIS is not, it's not something like, oh my word, it's totally new, totally different. I can't believe this. It's essentially the same thing as OSPF. It's got the areas. I mean, once you understand OSPF and you understand the basics about it, you pretty much understand ISIS. The reason it's much more difficult to understand is because of that second bullet on the screen. Integrated ISIS still requires an OSI address. Now, OSI addresses are different than IP addresses. They're weird, you might say, because it takes a second to look at them and really understand what they mean because we're not used to seeing them. But once you get used to that, and you can see right up on the screen, it's called a Connectionless Network Services, or CLNS address. Once you get used to seeing them, you're going to go, oh, well, that's not too bad. And it's not like you have to assign one to every interface like you do an IP address. Again, I'm getting ahead of myself, but I just wanted to give you some information around why it's more difficult. It's more difficult because people are used to TCP/IP, and when they see those addresses, it blows their mind. Well, let me throw a little bit of ISIS design at you so you can see some of the differences from the OSPF world. Now, looking at the diagram, kind of looks the same, right? Multiple areas, you can do summarization in the areas, but one major difference that you can probably see right now is there's no ABRs, the area border routers, or routers that are kind of sitting between the areas. Remember in OSPF we had the routers that just kind of sat here in between. One interface would be in area 2, one would be in area 3. Well, it's not that way in ISIS. In ISIS, a router is a member of only one area. As in, it can't be a member of multiple areas. It stays in only one. Instead of having ABRs, we have these things known as L1 and L2 routers. An L1 router is a router that maintains the routing topology, or maintains the topology database for only its area. For example, These two routers down here, L1 routers. All they do is know every single network that's in their area. Same thing here. Same thing up here. These routers just know what is in their area, all of the details about that area. Now, the L2 routers are considered backbone routers, meaning they only know about routes that are injected into the backbone. I'm kind of grinning when I say that because it's more than that, but that's what I'll say it for now. The L2 routers are the ones that just know about the backbone. They are considered backbone routers. The L1 slash L2 routers are routers that maintain a database for an area, meaning they know everything within the area, but they also know all the backbone routes. These are the L1, L2 routers in our domain, and those are the routers that comprise the backbone. If you notice in this picture, there is no area 0. Period. There's none at all. Because in ISIS, as I mentioned, there is no backbone area. Rather, there's just a backbone. You can see that we have level 2 routers that are linked together, and there's one in each and every area. That is what comprises the backbone of ISIS. If you were to color the backbone, we'd say it was right here. And we would say, whoop, a little scoliosis going on there. And then it comes down here, and we have a backbone right there. So the backbone really goes through all of these areas, and that is the only requirement, is that the backbone stretch to reach all of the areas. If we built another area over here and added some routers, into that area, we would stretch the backbone in some way to reach up to area 4, maybe is what this area is up here. And as long as we have a contiguous backbone, we meet the requirements of ISIS. This makes it more flexible than OSPF because we don't have everything needing to connect to this backbone area and all of these routers having to be a member of Area 0. The databases are kept completely separate. The level 1 database is maintained only within the area that the router belongs to. So all of these routers in Area 1, they're all level 1 routers of some sort. It's just this one has a level 2 database as well. They exchange that level 1 database within and only within that area. All the routers keep that. Now, once I do that, I might summarize that whole area, kind of like our ABRs do, into the level 2 database and have that passed across the backbone. So all the level 2 routers have an idea of what is in other areas without needing all the specific details. Now, when a level 1 router needs to reach another area, and you might be thinking, well, how does it do that? Well, it's going to send a message to its closest level 2 router because it knows that the level 2 router will be able to find the way out. Almost think of it like those level 1 routers are almost like clients. They know their way around their own area, but once they need to get out, they need a default gateway, if you will. They need a router that has the ability to get them to other areas, and that's where the level 2 routers come in. Let's get more into the facts, and then we'll jump back into the design. The first fact is that the metric of ISIS is not like OSPF. It's not based on the bandwidth. Rather, it's just an arbitrary value of 0 through 63, where 10 is the default. Every single link in ISIS has a bandwidth of 10, or I shouldn't say bandwidth, has a metric of 10. So this is 10, this is 10, this is 10. Every link is considered a cost of 10, which means you're going to have to get in and adjust things. Otherwise, it's going to be a very poor metric. Because if you look at it, I mean, in this case, if we had a network over here trying to reach a network over here, it's almost like RIP, right? That's all it is hop count, because it's going to say, okay, well, I've got a cost of 10 to go that way, or 10 plus 10, and that's 20 to go this way, even though this is the fast Ethernet links, and those will end up being faster than taking the top WAN T1 link. So we need to get in and create our own scale with ISIS to adjust those values manually. What I'd suggest if you plan on running it is to create a spreadsheet that says, okay, well, we'll say a cost of 0 equals maybe, a 10,000 gigabit per second link. A cost of 1 equals, maybe 1,000 gigabit link. And so on. I'm just giving, a goofy example here, but you have to define what these values mean because by default, they don't mean anything. They're just numbers that sit there. So you'll need to have a chart saying this is what I label the different link costs in my routing domain. Now, I know when I initially saw this, I thought, whoa, how lame. That means I'm going to have to go to every single link in my organization and type in how much that costs to ISIS. But if you think about it, don't you pretty much have to do that for OSPF anyway? It's just instead of typing in the ISIS cost, you're typing in the bandwidth of the links. Because the Cisco router doesn't accurately detect the bandwidth on most serial links. It just assumes they're T1 lines. So you have to accurately go in and set the bandwidth for OSPF to work. It just seems more logical to us to set the bandwidth than it does to set the ISIS costs. Now, granted, Cisco routers do detect the Ethernet links and fast Ethernet links correctly on the bandwidth values. So there is a little bit more work associated with ISIS. Add that to the fact that you have to create your own scale. Second, in OSI, the end systems, they were called ESs, would participate in routing by finding the closest IS to them. And that kind of communication was called ES to IS. It's kind of like we have DHCP nowadays, where we would assign a DHCP address and give a client a default gateway, which is the closest router to them that they would use to get off the network onto some other network. Well, in OSI's world, you didn't have a default gateway. The end systems, or PCs, that ran the OSI protocol were smart enough to actually discover, hey, there's a router here, and this one responds really fast to me. So that must be the closest router that I can use to get off the network, and they would auto-configure themselves. IP version 6 feature. They would figure their own way out to get across the network, and only recently has that been implemented in TCP/IP. Now, the reason I mentioned ES to IS communication, because obviously we don't use that in our world, is because later on we're going to see ISIS routing domains, and you'll need to know that kind of communication to understand how those domains work. Now, the level 1 and level 2 routers form like relationships and maintain completely separate databases. You will have L1 hello messages that are sent out and L2 hello messages that are sent out. An L1 router will not form a relationship with an L2 router over here. If I had an L1 saying hello, they would be like a different language, like Spanish is to me, where I would say, oh, I don't understand your hellos coming in. You're speaking a different language than me. So those relationships will not form. Now, if you have an L1 router communicating to an L1/L2 router in its same area, then it will form a neighboring relationship on an L1 level and will exchange routes between those two routers. Now, if you had an L1/L2 router in the same area as another L1/L2 routers, then at that point they would negotiate two relationships. An L1 relationship, which is kept completely separate. It's kind of a weird analogy. It just popped into my head. It's kind of like two schizophrenic people speaking to each other. Maybe these two people have dual personalities, to where totally separate personalities that each one has. It would be as if this guy thinks his name is Bob and Sam at the same time, and Bob negotiates a relationship over here with Fred, who also thinks he's Mike. Now, because of this dysfunctional relationship, Fred does not speak to Mike, and Fred definitely wouldn't form a relationship with Sam over here, but Sam might form a relationship with Mike. Does this make sense? That's kind of how this works over here. L1 and L2 are kept completely separate, to where the L2 portions of those routers will form relationships if they're in the same area. And then the L2s will form a separate relationship that, that does not bleed between. They do not speak and allow L1 to get in the way of their conversation. Now, if this L1, L2 router over here was in a different area than this one. At that point, they would only form an L2 relationship. The L1 relationship would not form because they're in separate areas. So that's the idea. That's how the communication works between those two levels of routers. Now, the last thing I want to mention is the L1 L2 rule. Just to compare and give you some frame of reference, an L1 L2 router is kind of similar to OSPF's ABR, the area border router, in the sense that you saw that topology, you saw the design. Those are essentially the routers that move packets from one area to another. The reason I consider them like an ABR is because the L1 portion is capable of talking to routers in the same area. It's capable of receiving packets from routers in that area and then sending them across the backbone to other areas. That's the same thing that the ABR did. When I first got into ISIS, one of the things that really threw me for a loop was understanding the place of an L2 router. I understood L1, that's a router just getting you around your own area. That makes sense. I understood an L1, L2 router, and that's a router that helps the L1 routers get to the backbone, get to other areas, but they can get around their own area as well. But just an L2 router didn't make sense, as in a router that knows the backbone but doesn't know its own area? That seems odd. Well, that's until I saw this design. This is actually a very common design with ISIS. Look at area 2 right in the middle. Area 2 represents the backbone. Now, it's not the backbone area like it is in OSPF with area 0, but you can kind of make that correlation in your mind. If you look, area 2 represents the core of the network. It represents the part of the network that everything connects to. In an ISP, that's their core routers, their biggest guns that they have on their network where all the traffic kind of filters through. All the other areas just connect in. Area 51 over on the left, 105 and 100 over here on the right-hand side. Notice that they have the typical design of an L1 router or multiple L1s router. They know their own area. And then you have an L1/L2 router. The goal or the responsibility of this router is to summarize area 51 into the backbone. Now, the backbone, these level 2 routers here, they don't know all the details about anything. They just get summarized routes. They know the summary of area 51. They know the summary of area 105. They know the summary of area 100s. Nothing detailed. As a matter of fact, they don't even know what's in area 2. They just know what's in other areas. This is where we've created an ISIS network with a true backbone. It meets the backbone requirements because if we were to color this, just like we did the other ones, you would see that you have a contiguous backbone, a link that is non-broken running through everything inside of the network. Now, in this environment, we would typically have redundant router connections. Now, I didn't draw them into place because I figured it would be messy enough as it is, but this router would typically be connected to that one as well. This one to this one. You'd have redundancy in place because otherwise, if one of those backbone routers went down, you can see just even physically speaking, we would lose a whole area of the network. We would lose 2 areas if this backbone router went down over here. So the redundancy is necessary. That's where we would typically have summarization coming from the areas into a dedicated core backbone. The last major concept I'll throw at you in this video is this concept of routing domains. Now, this is primarily just spoken about when people are referring to ISIS. There's these different routing domains which refer to where the packet's at. For example, if you were talking to somebody and they said, oh yeah, we're doing some level 0 routing, not that, people say this all the time, but level 0 routing would represent a connection or routing between the ES and the IS. That's all considered level 0. Level 1 routing describes routers that are passing information between ISs within the same area. Level 2 routing means that you're still in the same autonomous system. It's just now you've started to move data between multiple areas. And of course, the last one, level 3 routing, talks about leaving the autonomous system, leaving your ISIS routing domain to some other routing domain, and leaving networks under your control. In OSPF, level 3 routing would be considered passing data through the ASBR. Okay, that's it on the major concepts. I want to wrap things up by doing a line-by-line comparison of OSPF to ISIS to talk about the major advantages each one have, kind of like a boxing match. I'll try and keep my opinion out of it. It will be a little difficult because I really want you to have an idea of the advantages of each of these protocols. So first off, what they have in common. Both of them are linked state routing protocols. They both use concepts like areas that keep the topology databases manageable and separate. They have the topology database, the neighbor table, the routing table, the three tables that we talked about. Both of them use the same algorithm to calculate the best way around the network, and that's SPF. Now we'll expand a little bit more on that in the next video to find out. Oh, I'm keeping my opinion out of this. They do both use SPF. OSPF, when you design that network, the interfaces of the router belong to areas, allowing a router to exist in many areas, and those are considered your area border routers. In ISIS, no way. A router only belongs to a single area and has links that can get you to other areas, but the router itself does not belong to those areas. In OSPF, all areas have to tie to the backbone area. Area 0. That's part of your design requirements. Otherwise, you're using virtual links, which are a bad idea to begin with. ISIS causes the backbone to run to all of the areas rather than all of the areas coming to a backbone area, if that makes sense. I think seeing that design really helped solidify that point. All right, not too many punches thrown in round 1 of the comparison. Let's move into round 2. OSPF's advantages. OSPF supports more area types than ISIS. The whole concept of stub, totally stub, not so stub, all those area types we talked about with OSPF, those are OSPF things, and ISIS does not have that support. You can add that support, meaning you can configure it in a way to where the area acts like a stub or totally stubby area, but there's no command to type in where it's just nice and clean and simple to type in area stub. OSPF supports a metric scaled by default, meaning it reflects the bandwidth on the interface, and as long as you've configured the bandwidth statements correctly, OSPF will find the accurate, best way around the network. OSPF is supported by more vendors. It takes a special version of the IS or of the iOS to run ISIS. You have to have a service provider version or an enterprise version of the platform. You don't get ISIS support in just the standard iOS features. So OSPF is supported by more vendors and can be run, I guess you could say, cheaper because you don't have to purchase these special iOS versions to get it. OSPF, and in my opinion, the big punch OSPF throws here is well understood by the majority of the industry. Meaning, if you're looking for an OSPF technician, they're pretty easy to find. Somebody who understands Cisco will typically understand OSPF as one of their skill sets. ISIS, on the other hand, that's a skilled technician. That's kind of a specialty set of skills that that somebody would cultivate rather than just having, a standard set that OSPF is included in. That was a big round for OSPF. So let's move into round 3 and we can see ISIS's advantages. ISIS, number 1, handles updates more efficiently than OSPF. Rather than sending single link state update packets saying, hey, I've got an LSU with this LSA inside, oh, another LSU with this LSA, another LSU with all these individual updates, ISIS batches them, meaning if it has a bunch of updates, it'll send them all in the same packet if it can squeeze them all in there. ISIS rarely runs the SPF algorithm. Even though it's based on SPF, it only runs SPF to find reachability between OSI neighbors, so between routers. It runs a different algorithm called partial route calculation, it's known as PRC, to calculate IP reachability. PRC is much more efficient than the SPF algorithm, so really at its core, The algorithm that ISIS runs is more efficient for larger networks than the SPF algorithm as it was designed and is used in OSPF. ISIS is much faster by default to detect failures in the network, notify the network about it, and then converge. So if a network goes down and there's a backup path, ISIS will converge much faster to find that backup path and let the network use it than OSPF would. Now notice I put in parentheses by default. That's because OSPF can be tuned to be equal to ISIS in its convergence times, but you really need to know what you're doing with the tuning. You need to decrease the hello timers, you need to decrease the hold down timers. All of those timers that we saw with OSPF have to be modified in order to get the same speed as ISIS. It can be done, but it's just much more work. ISIS has less design constraints than OSPF because there is no backbone area concept. It can stretch between all areas. And finally, ISIS is very easy to adapt to IP version 6. OSPF had to be completely rewritten in order to handle the IP version 6 protocol, like we'll see later on in the series when we talk about IP version 6 itself. ISIS has been adapted already to run TCP/IP version 4, so it's not that much harder to adapt it to run TCP/IP version 6. It's just a different kind of payload it's carrying inside of its cache. And we'll talk about more of that when we get into the upcoming video. So those are the side-by-side feature comparisons. Now, I said I'd leave my opinion out of it, but I've got to throw one plug in there. I will tell you, in my humble opinion, I think ISIS is better for the most part. The reason I say that is because you haven't seen the OSI addressing yet. We'll see that in the upcoming video. Once you see that, you're going to go, whoa, that's weird. and it takes a sec to get used to. When I first saw it, I have to admit, I was like, this ISIS, it's for the birds. Nobody should use this thing. Until I actually set it up a couple times, and then I was like, hey, this is pretty simple. It's all concepts. When you see the config, you're going to be like, wow, this really is simple. But it's understanding that OSI address that really makes or breaks this protocol. For now, that's enough concepts for one sitting. Let's wrap up. We first off defined what is, what ISIS is all about. And we looked at its history, where it came from. It was originally developed to route for the OSI protocol. And we talked about why it's even in use today. It's because the government mandated that all ISPs had to run both protocols for a season, and that season keeps extending longer and longer and longer, at least for the ISPs that chose to stick with ISIS. We then looked at the design of ISIS, very different than OSPF. Still uses the area concept, but instead of having ABRs and ASBRs, we have this level 1 and level 2 routing characteristic we have to get used to. Finally, we looked at a side-by-side comparison of ISIS and OSPF. OSPF giving some very big advantages, but also ISIS offering some competitive advantages on its side. You have to choose one or the other because most of the time, organizations will not want to run both of them. I hope this has been informative for you, and I'd like to thank you for viewing.